Great to see you here. We are talking again about number theory and cryptography. And in this session, we will be looking at primes and trial division. Now, when we look at prime numbers, they have a very important role in division of integers and, of course, in cryptography. Now, when we've been looking at prime numbers, they're already known in ancient times. And people have been proving a lot of things about prime numbers. For example, one of the elements, properties of prime number is that there are an infinite number of primes. Another element that came from the study of prime numbers is what we call the golden ratio. Over the last 400 years, many interesting and important properties have been identified of primes, and they will be very important in computer science, and we will look deeper into them. Now, some of those properties, in fact, relate to the property that any integer can be written as a non-decreasing number of primes, a product of a non-decreasing number of primes. So we will look into that and we'll try to find out what those prime numbers are, and we use it later in some exercises. Now, when we look at cryptography, there it is very important to have large prime numbers. Now, what happens is when we have large numbers, we want to factor them, and we want to factor all those numbers into large prime numbers. It means that it takes a lot of time to do this, and this is one of the properties of cryptography, or the elements you want to have in cryptography, is that it will take a very long time before people can decipher the message that you send, or by the time that you decipher it, it's not valid anymore. An element that's happening also when you are looking at cryptography is the changing of the keys, so that the algorithm that's being used, or the people who are looking at the messages and try to decrypt them, that they always encounter problems because the key basically has been changed. Now, when we look at the primes, we first have to define them properly. So a prime is in fact any integer larger than 1, which has the only positive factors are 1 and the prime number itself and the number itself. A positive integer that is greater than 1 and that is not prime, we call it a composite. And we call it a composite because we can multiply it, or we can write it as a multiplication of primes. So once you have a prime number, any prime number, larger than 1. 1 is not a prime number, but 2 is a prime number. So there are two factors that divide 2, 1 and 2 itself. So basically, that's the definition of a prime number. Now, we have some prime numbers. There are infinite number of prime numbers, so you can find lists of prime numbers. People are finding more and more prime numbers every day. Of course, it becomes a little bit more difficult because we have a lot of prime numbers that have been identified, and it needs a lot of computer power. Now, some prime numbers are, for example, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31. And of course, the list continues. You can find a list of prime numbers on the internet, and you can keep them somewhere when you are doing some calculations. But it's very easy to find them. And of course, the list is growing constantly. Now, based on this, we can define what we call the fundamental theorem of arithmetic, which says that every integer greater than 1 can be written uniquely as a prime or as a product of 2 or more prime numbers, where the prime numbers are written in order of non-decreasing size. Now, non-decreasing size means that we may have repetitions. So we may have a number, when we look at the series of prime numbers, we may have a repetition, for example, of 11, and that's mean non-decreasing order. So or we can use them in non-increasing order. Both are possible. So typically, it depends how we are writing the numbers. Now we can see here I write it in non-increasing size, so they're always increasing. I write 368,445 is basically the product of 3, 5, 7, 11, 11, and 29. So we have in fact the repetition of 11 in this case. Based on this, we can identify the composing primes of each integers, and we will call that factoring the integer. Basically, factoring the integer is writing the integer as a product of primes, and any integer can be written as a product of prime numbers. When we look at trial division, we try to find that an integer is prime, and we can use certain observations. When we have n, an integer, to be a composite integer, then n has a prime divisor. So basically what we can say that prime divisor has to be less than or equal to square root of n. So it means that when we have a number, for example 100, we know that it has a prime divisor less than or equal to square root of n, less than or equal to 10. Now 10 is not a prime, but 7 is a prime. So basically we can say that when we look at 100, we can write it as a product of prime numbers between 2 and 7. Now, the way to do this calculation is what we call a brute force algorithm, and that brute force algorithm is called trial division. And it's based on the property that when an integer is prime, it is not divisible by any prime less than or equal to its square root. So we have to find that square root. Now, when we look at the number we considered before, we can take the square root of it, and we find that the square root of 368,445 is equal to 606, almost 607. So we can say that the primes have to be smaller than 606, and we can consider the list 2, 3, 5, 37, and so on. So we can continue that list until we come close to 606. 606 itself is not a prime, but there will be a closer prime that we can consider. Now we can start dividing the number by the lowest prime. Now we can already see when we look at the number, it's not an even number, so we cannot divide it by 2. So we go to the next prime number, which is 3. So we try to divide it by 3, and it gives us an integer which is 122,815. So basically what we're going to do now is to try again with number 3, with the prime number 3, see if it's divisible. If it's not, we go to the following prime number, which is 5. Let's have a look at it here when we look at the exercise. So we divide the number by 3. Now it means that the remaining number is 122,815, and we can apply the rule of square root of n again here. So when we take the square root of 120,815, we see that this is 350. So when we are dividing 122,815, we see that the largest prime that we can use has to be smaller than 350. We divide by 3 again, but we can see that it doesn't work, and we find divided by 5, so we find 24,563, and when we take the square root, we see that the number decreases. Now we come to 156. 156 is clearly not a prime number, but it's an even number. So we go again, another division by 5 is not possible, but we can go to the next prime number. So we find when we divide by 7, it's 3,509, and we see that we're already coming closer to the let's say more acceptable prime numbers. 59 is a prime number, so we can continue. Another division by 7 is not possible, so we go to 11, and we find 319, which basically says that the next prime that we can divide is smaller than square root of 319, which is 17. So we divide it again by 11, and we find the final number, which is 29, and we know that the number 29 is a prime number. So basically what we find here is that division, and now we're going to do a second exercise with the number 2310. We divide by we take the square root, so we consider all the primes smaller than 48, and we start with 2. So we find 2310 divided by 2 is 1155. Now we already see we cannot divide by 2 anymore because we don't have an even number. So we divide by 3, when we find 385. We take the next prime numbers, which are 5 and 7. So when we have 5, we find 77. And 77 divided by 7 is 11. So basically, we can write a composed number as 2 times 5 times 7 times 11. So basically, that's what we do with the trial divisions, and that is what we want to find basically. Now, the algorithm, you can see, it's a brute force algorithm when we have larger numbers and when the numbers grow larger and larger, that this can take up a lot of time. So basically, this is what I wanted to talk to you about prime numbers and how to factorize integers as a product of prime numbers. In the next session, we will look at the sieve of Eratosthenes. I always have a problem saying this name. It's not an easy name, but let's say it again, Eratosthenes, which is a way how to find the prime numbers in a group, let's say within a zone, within a set of numbers that we have, and it's very easy to find those prime numbers. You're doing a great job, and I'm looking forward to seeing you in our next presentation and video. Thank you, and bye-bye.